Hello everyone. In this video I'm going to be covering the topic 312 amount of substance from the AS level AQA Chemistry syllabus. As always, the presentation will be available in the description of this video. Let's begin. The first thing you have to know from this topic are two definitions. The first one is relative atomic mass, often labeled AR. Relative atomic mass is the average mass of an atom of an element relative to 1/12 of the mass of carbon-12 atom. I am saying average mass because relative atomic mass takes into account the isotopes of the elements, including their masses and abundances. You can see on the right side of the screen a copy of the periodic table that will be given to you on the exam. You can see that every element has a relative atomic mass which is given to one decimal place. Relative molecular mass, labeled MR, is the average mass of a molecule relative to 1/12 of the mass of carbon-12 atom. Relative formula mass may be unfamiliar to you, but it is a fairly simple concept. You know that ionic compounds do not have molecules, and instead they have ionic lattice structure, which form a crystal. And because of that, relative molecular mass do not work with them, because they can only be used for molecules. Instead, ionic compounds have relative formula mass, which is defined as the average mass of the formula unit relative to 1/12 of the mass of a carbon-12 atom. A formula unit is the smallest unit of a non-molecular substance. Example could be an ACl or any ionic substance. Moving on to moles. Avogadro's number, which was ironically not discovered by Avogadro, is the number of particles in 1 mole of a substance. It is equal to 6.022 times 10 to the power 23. In order to understand Avogadro's number, you have to know that Avogadro's number is just a number, and there is no magic in it. Avogadro's number is just like any other number, like 4, 7, or 100. It is labeled n lowercase a. When you have Avogadro's number of particles, you have 1 mole of particles. I'm saying particles because it can be literally anything. Atoms, molecules, ions, electrons, elephants, whatever you want it to be. For example, 1 mole of sodium atoms has 6.022 times 10 to the power 23 sodium atoms. 1 mole of carbon dioxide molecules has Avogadro's number of carbon atoms and 2 times Avogadro's number of oxygen atoms, because in each CO2 molecule there are 2 oxygens. Let's think of sodium atoms again. Each sodium atom has 11 electrons. How many electrons would I have in 1 mole of sodium atoms? If you said 11 times Avogadro's number, then you are correct. You can use the formula on the right side of the screen to find the number of moles in a substance. Number of moles is equal to mass of a substance divided by its molar mass. Moles have no units, mass has unit of grams, and molar mass has units grams per mole. When something is dissolved in a solution, you can use the formula at the bottom of the screen to find the number of moles dissolved. C equals to N divided by V, where C is the concentration of the solution, N is the number of moles, and V is the volume. Be careful with units here. Concentration has units moles per decimeter cubed, and volume is measured in decimeter cubed. You can use this formula to find the number of moles dissolved in a solution, provided you know the concentration of said solution and its volume. Moving on, we have ideal gas law. In IGCSE, you must have come across the fact that at room temperature and pressure, gas occupies 24 decimeter cubed volume. Ideal gas law is an extension of that rule, because using it, you can calculate the volume of the gas at any temperature and pressure. I am saying ideal gas law because it can only be applied to ideal gases. What is an ideal gas, you might ask? Well, the ideal gas is a theoretical gas, in which gas particles are not subjected to any intermolecular forces, meaning that all particles are in complete gaseous state. Even though it is impossible, in normal conditions, basic gases such as oxygen, carbon dioxide, nitrogen oxides behave almost completely as ideal gases. So an ideal gas law can be used to approximate their properties. The ideal gas law states that PV equals nRT, where P is the pressure measured in pascals, V is the volume measured in meters cubed, N is the number of moles of gases, R is the gas constant, which you will be given on an exam. It is equal to 8.314, and T is the temperature measured in kelvins. In order to convert from Celsius to kelvins, you have to add 273 to your temperature in Celsius, and you get temperature in Kelvin. Remembering the formula and the units is 75% of the work when solving questions involving the ideal gas law. If you just convert data given in the question to the right units, you will be given a mark for that. So I strongly suggest that you remember all of the units for the equation and the equation itself. Let's do a past paper question that involves the ideal gas law. In the first experiment, liquid Y is injected into a sealed flask under vacuum. The liquid vaporizes in the flask. The table below shows data for this experiment. Calculate the relative molecular mass of Y. So straight away, we are told that the liquid vaporizes in the flask, so we can use the ideal gas law. In order to calculate the molar mass, we can calculate the number of moles of Y using the ideal gas law equation. And since we already know the mass of Y, we can use this equation to calculate the molar mass of Y. Let's look at the data provided. Volume and pressure are given in the wrong units, so they need to be converted. In 1 meter cubed, there is a million centimeter cubed. So in order to convert from centimeter cubed to meter cubed, you need to divide your value by a million, or multiply by 10 to the power of minus 6. Pressure is given in kilopascals. To convert to pascals, you just need to multiply by 1000. Rearranging the ideal gas law for the number of moles, you get N equals pressure times volume divided by the gas constant times temperature. Substituting the data, we get 0.001 number of moles. Knowing the mass and number of moles, we use the formula from the previous slide to get the relative molecular mass of 72 grams per mole. Empirical formula is the simplest whole number ratio of atoms of each element in a compound. For example, dodecane, which has a formula C10H22, has an empirical formula C5H11. You have to know that formula of ionic compounds is always empirical. Molecular formula shows the actual number of atoms of each element present in a compound. Let's do a past paper question. Calcium dihydrogenophosphate can be represented by the formula Ca in brackets H2PO4 X, where X is an integer. A 9.76 gram sample of calcium dihydrogenophosphate contains 0.17 grams of hydrogen, 2.59 grams of phosphorus, and 5.33 grams of oxygen. Calculate the empirical formula and hence find the value of X. To approach this type of problem, you have to know that empirical formula, by definition, is the ratio of atoms of each element in a compound. So in order to find it, you can calculate the number of moles of each element present in the compound and find their ratios. Luckily, you are told the masses of almost every element in the compound, and in order to find the mass of calcium, you can just subtract the masses of hydrogen, phosphorus, and oxygen from the mass of a sample, and it will give you the mass of calcium. To find the moles of each element, divide the mass of the element by their relative atomic mass. This is what I did here. And then, I found the ratios of moles of each element by dividing the number of moles of each element by the number of moles of calcium, which turned out to have the least number of moles. At the end, I got the empirical formula CaH4P2O8, and as you can see, H4P2O8 has a common factor of 2, and if you take it outside the bracket, you will have the molecular formula of calcium dihydrogenophosphate, so X is 2. Balancing equations. Before doing any moles calculations, which involve a reaction, you have to make sure that the reaction is balanced so that the atoms are reacting in correct ratios. Let's do a past paper question. The percentage of copper in a copper 2 salt can be determined by using a thiosulfate titration. 0.305 grams of copper 2 salt was dissolved in water and added to an excess of potassium iodide solution. The iodine produced was then titrated with the sodium thiosulfate solution. we are asked to determine the percentage of copper by mass in the copper-2 salt. In order to calculate the mass percentage of copper in the copper-2 salt, you need to divide the mass of the copper by the mass of the salt. Luckily, we are already told the mass of the salt, so we just have to determine the mass of the copper in it. When the copper salt was dissolved, the copper ions reacted with the iodide ions and produced iodine. So we can calculate the mass of the copper in the salt by calculating the number of moles of copper ions. In order to know the moles of copper ions, we can calculate the moles of iodine produced. Since we know that the produced iodine was titered against the sodium thiosulfate solution, we can calculate the moles of iodine from that reaction. We know that titration required 24.5 cm cubed of 0.1 mole per decimeter cubed solution of sodium thiosulfate. We can use this equation to calculate the moles of thiosulfate. First, we convert centimeter cubes to decimeter cubes by dividing 24.5 by 1000. Then we multiply it by the concentration, 0.1, to get the number of moles, 0.00245. This is the number of moles of thiosulfate ions. We can know the number of moles of iodine if you have to look at the ratios. They are 2 to 1. So to calculate the number of moles of iodine, we divide the number of moles of thiosulfate by 2. So 0.00245 divided by 2, if you round the answer, you get 0.0012. So we know that 0.0012 moles of iodine were produced in the first reaction. Looking at the ratios again, from 2 moles of copper ions, 1 mole of iodine is produced. So the number of moles of copper is 0.0012 times 2, which is rounded equal to 0.00245. Finally, to calculate the mass percentage, you multiply the number of moles by the relative atomic mass of copper and divide the result by 0.305 to get the mass percentage of 51%. For the exam, you have to be able to write ionic equations from reactions. An ionic equation is an equation that shows only the reacting ions that produce the product. To write an ionic equation, you have to follow these steps. First, write a full balanced equation of the reaction. Second, split the aqueous compounds into ions that compose those compounds. And third, cancel out ions that appear on both sides of the equation. Those are called spectator ions. Let's look at an example of an ionic equation of the reaction between silver nitrate and sodium chloride. First step is to write a full balanced equation. Silver nitrate plus sodium chloride goes to silver chloride plus sodium nitrate. Luckily, this reaction is already balanced, so we are ready to move on to the second step. In the second step, we split the soluble compounds into the ions. Silver nitrate splits into Ag plus and NO3 minus, NaCl splits into Na plus and Cl minus, and on the right side of the equation, AgCl does not split because it is insoluble, it does not dissolve, and sodium nitrate splits into Na plus and NO3 minus. Third step, cancel out the species that appear on both sides of the equation. Sodium ion appears on both sides, nitrate ion appears on both sides, so they are cancelled out. We end up with Ag plus Cl minus react to form AgCl, which is the ionic equation for this reaction. Hydrated salts. Hydrated salts occur when water molecules are enclosed in the ionic lattice crystalline structure. They are not chemically bonded to the compound, so water is not included in the formula, but it is still shown as a separate compound when writing the formula of the hydrated salt. The general formula for hydrated salts is m.NH2O, where m is the ionic compound, n is the number of water molecules enclosed per each salt molecule. You have to be able to differentiate between the terms hydrated and anhydrous. Anhydrous salt is the one that does not contain water of crystallization. Example 1 would be anhydrous copper sulfate. On the other hand, hydrated salt would be the one with water crystallization in its structure. Example would be copper sulfate pentahydrate, where pentahydrate represents the 5 water molecules in the crystal. Atom economy. Atom economy is a measure used to rate the reaction based on how efficiently it converts reactants into the required product. If you have high atom economy, this means that most of the reactants are converted into the required product. Atom economy is calculated using this formula, which is total molecular weight of desired product divided by the total molecular weight of all products. Let's look at an example of fermentation of glucose. During the fermentation, one molecule of glucose ferments to produce 2 molecules of ethanol and 2 molecules of carbon dioxide. Assuming that the desired product is ethanol, the atom economy would be 2 times relative molecular mass of ethanol divided by 2 times mR of ethanol plus 2 times mR of carbon dioxide times 100%. This gives us the atom economy of 51%. Why is having high atom economy beneficial? Having high atom economy would mean that most of the products are used and small amount of waste product is made, which means that there is less waste to dispose of, which is beneficial to the environment. Also, when atom economy is high, this means that most of the reactants are turned into products, which means that factories do not have to buy a lot of raw materials to produce the same amount of product. This has economical benefits. Percentage yield. Percentage yield is different to the atom economy. Percentage yield measures how effective a reaction is at converting reactants into products. To get the percentage yield, you divide the actual yield by the predicted yield. The percentage yield can only be calculated if you conduct the reaction in the laboratory and get the actual yield. Actual yield is always lower than theoretical because side reactions occur which consume reactants. Reactants or products can be lost when they're transferred during a multi-step reaction. The reaction sometimes can be unfinished, meaning that not all reactants have been turned into products. This is the end of the topic of amount of substance from the AS-Level AQA Chemistry syllabus. To check out other topics, please see other videos available on my channel. The next video will be about the topic of bonding. See you next time.